Yes. Thanks. I have just started recording. Okay, so benzene with an OH group is phenol. It's called phenol. Okay. It's not called benzol or anything. NH2 is an amine group. I have briefly mentioned, yes, we have come across amine like ethylamine, propylamine, but not so much. We haven't really covered it as a functional group, which we will do this year. It's called a phenylamine. Okay, do not get this confused with NO2. NH2 is an amine and O2 is a nitro. Okay, NO2, nitrobenzene. NH2 is a phenylamine. So the phenyl represents the benzene ring. Okay, the next one is phenylethene. All right, why do we not call this ethene benzene? Now it sounds a little bit funny, because if you write it as ethyl benzene, that looks like two carbons that have single bond, ethane. Okay, in this case, it's an ethene. So to show that it's an ethene, you put the ethene at the end, and then the benzene is the side group. So when benzene becomes side group, it is called phenyl. Next, now you have 1, 2, 3, 4 carbons. So that looks like butane, butyl benzene. However, the problem is the benzene group is hanging off on the second carbon. So I hope you can see here that the benzene ring is actually your side group, and that's your principal chain. To name this, we call this 2-phenylbutane. So that means the benzene, the phenyl, is hanging on the second carbon of your butane. How is it different from ethyl benzene? The benzene is at the very end. It's on the first carbon, so we don't have to worry about the numbering system. Okay. Here, we need to take into account of the position of the benzene ring, and it turns out that the benzene ring is a side chain or a side group, and the principal chain is the butane. Next is a ketone, C double bond O, attached to a carbon and attached to a carbon, another carbon. So this functional group is like a ketone. So we call it phenylethanone. Okay, the ethanone is the name of the ketone, two carbon, and then phenyl is the benzene that is hanging off as a side chain. Last one is again an ester. It's a different ester from the one that we saw before this, because this time the benzene is the one attached to the alcohol. So the benzene ends with YL, and this other part ends with OH. So this is an ethanoate. Okay, we don't call it a benzyl ethanoate, we call it a phenyl ethanoate. Right. Please make sure you copy all this. Please do not worry too much about the naming. Okay? If you're still trying to work out why is this called phenyl, then why is the other one called benzene, as you go along, you will see that some name sounds more familiar than the other. Okay. As long as you know the basic stuff, like especially the functional group, like phenylamine, phenol, benzoic acid, nitrobenzene, chlorobenzene, bromobenzene, iodobenzene. These are the basic ones. Okay, but when you start having this hanging off, that's a little bit less commonly asked in the exam. Next, This is when you have more than one groups attached, so it gets more complicated, but then again, do not stress much on it. So if two or more substituents are present on the benzene ring, their positions must be indicated by the use of numbers. This should be done to give the lowest possible numbers to the substituents. When two or more different substituents are present, they are listed in alphabetical order and di, tri prefixes should be used. So this time, the standard nomenclature rules apply. The naming system that you have learned last year when we came to name organic molecules. Okay, so that means when you assign number, you want the side chains to have the lowest number. Okay, if you only have a benzene ring or if you have one substituent, it's easy to number them. For example, if you see a benzene carbon, it's 6 carbon, you can start your numbering anywhere. You can call this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, or you can start carbon 1 here, 2, 3, 4, 5, 6. You can start carbon 1, 2, 3, 4. They're all the same. Okay, because in a benzene, all the carbons are the same. However, they start to change when you have a side chain or a side group, right? So automatically, when you have a CH3, obviously you want the methyl group to be the lowest number. So you would call this carbon 1. Which side do you go? It doesn't matter at this point. Carbon 1, 2, 3, 4, 5, 6, or carbon 1, 2, 3, 4, 5, 6 is the same, as long as methyl is number 1. Don't start calling this number 1, 2, 3, 4, 5, 6. That's wrong, because your carbon 1 is here and then your methyl is number 2, when you can actually call this carbon number 1. So let's see, when you have more than one, right? So you have a methyl group and a chloro. Naming them should be alphabetical as well, okay? So we call this a 2-chloro-methyl benzene. Sometimes accepted answer is, no, okay. So the only accepted answer is a methyl benzene. Why? Because methyl benzene is the functional group. Okay, so that is automatically carbon number 1, and then you can either go here 2, 3, 4, 5, 6. That makes your chlorine number 6, or you can start from clockwise direction. 1, 2, 3, 4, 5, 6. Okay, so we call this a 2-chloro-methyl benzene. Next, I think you know what's coming. The principal chain is a chlorobenzene. 1, 2, 3 chloromethyl benzene. Okay, you do not want to start counting anti-clockwise, because otherwise 1, 2, 3, 4, 5, your chloro will be number 5, and it's either number 3 or number 5, so obviously you would choose number 5. Okay, so that name is, sorry, we call it a 3-chloromethyl benzene. And I think it's getting quite obvious. The next one is a 4-chloromethyl benzene. I am missing an E there. Okay. The last one, you have 2 methyl groups. Okay. So this is a dimethyl. 1,3-dimethyl benzene. So which one is number 1? It doesn't matter. Okay. You can take this one number 1. 1, 2, 3. Okay. 1,3-methyl benzene. Don't call it 2, 3, 4, 5. 1,5-methyl benzene. That's wrong. What if I choose a different numbering system? Say I call this number 1, the pink. Okay, 1, 2, 3. Same thing, right? So whether you choose top 1 as number 1, bottom right as number 3, same thing. Naming is 1,3-dimethyl benzene. If you take the bottom right as number 1, the top one becomes number 3. So 1,3-dimethyl benzene still. I hope that's okay. So please copy this down. So the green system of numbering and the pink system of numbering will give you the same answer. It doesn't matter which one you choose. But what's wrong is if you take 1,5. 1,5-dimethylbenzene is wrong because 1,3 is smaller. And same thing, same rule applies when you have number between each other, there's a comma, and between number and a letter, there's a dash. Okay, moving on. Oh, there's more. Now, the main group here is the phenol. That's the principal chain. Okay, so phenol will be number 1, 2, 3, 4, 5, 6. So it's 2, 4, 6 bromophenol. Okay. Oh, tribromophenol. Sorry. 2, 4, 6 tribromophenol. If you start counting in an anti-clockwise direction. How about, if you start counting in a clockwise direction, how about you start counting in an anti-clockwise direction? I will use green. Same thing, phenol is your principal chain. Phenol takes number 1, 2, this one is 4, 6. You still get 2, 4, 6 tribromophenol. So you have to look at both directions. When you go clockwise or anti-clockwise, sometimes it's the same. Sometimes it will give you smaller number. Okay, how do you know who is the principal chain? Well, you only know this based on experience. Okay, so the more molecules of benzene you meet, the more familiar you are with their names. Next, you have a carboxylic acid group and a phenol group. So between carboxylic acid and a phenol, carboxylic acid wins. So that's your principal chain. So that means your OH is the side chain. OH as a side chain is called hydroxy group. Okay, so carboxylic acid. Now a hint is from last year you already saw that. Oops, where is my cursor? From last year you already said that the carbon of a carboxylic acid has to be number 1. So this is carbon 1, 2, 3, 4. 4 hydroxybenzoic acid. That's clockwise direction. If you go anti-clockwise, 1, 2, 3, 4. Same thing. Okay, so that's why sometimes in most cases that your benzene ring will give you the same number. But the most important thing is you need to know who is number 1. Okay, now next you have a benzoic acid and a nitro group. Okay, so your benzoic acid will win. So your nitro group is the side group. Benzoic acid will take number 1. You can, you will go from clockwise direction, so that becomes carbon number 3. Do not go anti-clockwise because anti-clockwise is a longer route, 2, 3, 4, 5. So if you start counting in an anti-clockwise direction, it will be 5 nitrobenzoic acid, where if you go in the clockwise direction, it is 3 nitrobenzoic acid, and there could only be one answer, which is 3 nitrobenzoic acid. Okay. Moving on. Where's my cursor? Right. Next is the chemistry, the chemical reactions of arenes or benzene. Okay. All right, so first we look at the structure of benzene first. Benzene, even though there is a double bond, it does not undergo the same reaction like alkenes. Alkenes undergo electrophilic addition reaction. Okay, but benzenes, whether it's methylbenzene, chlorobenzene, nitrobenzene, as long as you have that benzene ring, it will undergo what we call an electrophilic substitution. Okay, most of benzene's reactions involve substituting one hydrogen atom for another atom or groups of atom, right? I'll talk about that later on. Why do we have substitutions? Because that delocalized system is stable. When you add things to the benzene ring, you will break the delocalized system temporarily, but at the end of the reaction, the delocalized system will reform back, okay? And the only way to reform this delocalized system is by kicking out the hydrogen, because remember, each carbon atom in your benzene ring can only hold one more side chain, okay? You'll look at the structure later on. The reason why we attract electrophiles is the same reason why alkenes attract electrophiles, because benzene has a high electron density above and below the ring. Same thing like alkenes, there is a high electron density above and below the double bond. Okay, so the characteristic reactions of benzenes are electrophilic substitution reaction. Okay, so I am going to share my other device because that's where I use to draw. How do I iPad? Hold on, yeah. Okay, can you see the screen where it says recapping?
Yeah.
Okay, good, thank you. So before we look at the mechanism of your benzene, I just want to recap the mechanism of alkenes. Now, even though I said that benzenes and alkenes have different mechanism, but you know, still they have some sort of similarity. Now for alkenes, let's see, where's my pointer for this one? Okay, so for alkenes, it is an electrophilic addition reaction. They still attract electrophiles, okay, because of the rich electron density above and below the double bond. Okay, that red thing is my pointer. Okay, so what happens is the double bond will attack the electrophile. Electrophile usually has a charge of positive. Okay, so the double bond will break. One of the double bond will break. It attacks the electrophiles, and then it forms a new bond with your electrophile. Okay, so that C single bond E is the new bond. Remember, this double bond is broken, so the carbon, this first carbon has 4 substituents already. This other carbon only has 3, if you can see. 1, 2, 3 bonds. Okay, so if you still remember, whoever gets the electrons will become negative, and whoever doesn't get the electron will become positive. So that positive charge is on the carbon atom that has nothing, that hasn't got anything hanging off it. Okay, so the next step is for the nucleophile, which is the bromide ion, to attack that positive carbon. Okay, because this nucleophile has a lone pair of electron. Bromide ion as a nucleophile can donate its lone pair of electrons, and the charge, positive ion and the negative ion, cancel out. Okay, so you will see the CBr bond. That's the last bond being formed. So that's alkenes. Okay, next we want to look at benzenes, right? I still have my alkenes on top for you to compare. Now, the way that I have drawn the mechanism of benzenes, this is not how I expect you, or how CIE expects you to draw it. Why? Look at the structure of the benzene. It is drawn as a hexagonal ring with alternating single double bond. That's not how you draw your benzene. Your benzene should be, it should draw a delocalized system inside the ring. Okay, but I will show you, for the sake of comparing alkenes and benzenes, how similar they are. Okay, so what happens? Your benzene is rich in electron density, therefore it acts as a nucleophile. It attacks an electrophile which has a charge of positive. Okay, so I have less than 10 minutes left. So the double bond attacks the electrophile. Now the electrophile can choose whether to be attached to this carbon, first one, or the second one. Okay, it doesn't matter at this point where is it attached. It doesn't matter. Okay, so I just like to draw generally my incoming electrophiles to be on this right side, top right. I don't know why. Okay, you can always write it here. Now same thing. Oh, you shouldn't have that E plus. You shouldn't have that plus sign anymore. Okay, because once it gains electrons, the electrophile becomes neutral. Okay, so because the positive charge goes to the other carbon. So this carbon accepts the electrophile. Okay, this carbon is happy to have 1, 2, 3, 4 bonds. Okay, the other carbon only has 3 bonds. And if you look at the alkene above, the carbon that has 3 bonds is the one with the positive charge. Same thing in the benzene. The one with 3 bonds is the one that has a positive charge. Okay, or to say it, wherever the electrophile sits, that's happy already. The carbon is happy. So the other carbon will develop the positive charge. Okay, next, talking about delocalized system. I said the delocalized system is stable, so you have to restore the delocalization. Okay, that means you can't have this positive charge in that ring. You want the double bond back. So how can you, the only possible way to reform the double bond is for this carbon-hydrogen bond to break. The electrons from the carbon-hydrogen bond is donated to this positive carbon. Okay. When you donate electrons into the positive carbon, that's where you have your double bond. Okay, so that's the only difference, right? This carbon in alkene, the positive carbon in alkene, is stabilized by an external nucleophile. But in your benzene, this positive carbon is stabilized by breaking the carbon-hydrogen bond. Remember that in your benzene ring, there could only be one atom or one bond hanging off the ring. So electrophile comes in, hydrogen has to go. Okay, right. Now, I don't want you to draw it like this because you are not really drawing the delocalized system. You are drawing single, double, alternate, in alternate arrangements. Okay, the way you draw it is in the next one. Oops. Next page. Okay, so I've totally omitted the mechanisms of alkenes. I will now combine the mechanism, the drawing of the mechanism when you draw the double bond like that, fixed, and compared to drawing the double bond as a delocalized system, which is a circle in the inside the ring. Okay, so I don't know if you can see it, but there is some small numbers there, 1, 2, 3, 4, 5, 6. At the moment, when it is as a benzene, it doesn't matter which one you call it as carbon 1 or carbon 2. Okay, so what happens? Here you can see it's the double bond that is attacking the electrophile. Same thing here, the double bond is now a circle. We just don't know where, right? You can actually use, you can actually put the electrophile, I'm missing a positive charge there. You can actually attack the electrophile between carbon 1 and 2, between carbon 2 and 3, 3 and 4, 4, 5, 5, 6, 6, 1. It does not matter. Okay, so I like to attack it between carbon 1 and 2, which is this top bond, right? So same thing, the delocalized system of electrons attack the electrophile. The electrophile just need to choose where it wants to sit, carbon 1 or carbon 2. And as I said, I like to draw the incoming electrophile to sit on carbon number 2. There is no specific rule that says it always sits here. Okay, it can sit here, it can sit here, 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 or here, right? But remember, if you compare it to the above diagram, the positive sign is on carbon 1. Okay, if this is 1, this is 2. Electrophile sits on carbon 2, the positive sign is on carbon 1. This time, the positive sign is delocalized inside the ring. Okay, there is no specific, I do not put the positive sign on a specific carbon. However, the way you draw the ring, this one, it's now broken, right? Because you already break the bond. The ring has to extend between carbon number 1 until carbon number 5. Okay? Why is that? Because you are breaking the carbon 1 and 2 system. Okay? So I'll talk about that again shortly. So again, the next one is you want to restore the positive charge. The delocalized is broken. The delocalized system is broken at the moment. So to restore the delocalized system, the only way you can cancel out a positive is by adding something negative to it. Okay, positive, negative, cancel out, neutral. So how do you get the negative part to cancel out this positive? Is the carbon-hydrogen bond. So you want to break the carbon-hydrogen bond. The electrons from the carbon-hydrogen bond is given to the positive charge. Okay, so then you got your delocalization restored and you have your electrophile. Your hydrogen is no longer there because each carbon can only hold one thing. Okay, don't forget there is hydrogen in this other carbon because you haven't done anything to it. Only this carbon has lost its hydrogen because it is being replaced by the electrophile. This is the substitution. Okay, now once you have the electrophile, obviously this carbon automatically becomes carbon 1. It has to be carbon 1. Why? Because you want it to be the lowest number. So one thing I forgot to mention is that when this carbon-hydrogen bond breaks, the bond goes to the oxygen, the bond goes to the inside of the delocalized system, the broken delocalized system. The hydrogen becomes H+. Okay, why? You should already know why. Okay, so this is what you have in your notes. Right, so we only have less than a minute. So I want you to, when this call ends, when this session ends, I want you to read this part again. Okay, you don't have to copy. So you can see that here, they put the one that is in your notes, they put the electrophile on carbon number 1 on the top, which is not a problem. Okay, and another thing that you need to take note of that is because the carbon number 1 and number 2 is affected. So your broken delocalized system extends from carbon number 2 to number 6. Okay, and then to restore that broken delocalization, the carbon hydrogen breaks. So you have only the carbon electrophile bond left. Okay, don't forget that you have carbon, you have hydrogen on carbon number 2, 3, 4, 5, and 6. It's just not drawn because it is a skeletal formula. And the other product you will form is hydrogen ions. Okay, so I think I will get cut off anytime now. So please make sure you read this part. Okay, I will recap back tomorrow, in tomorrow's session. I will start from this slide again. Okay, right. Okay, Assalamualaikum and thank you everyone. That is all for today.